It's Ms. McClellan again, here to go over our notes with you. This is IM2 6.1.2. How can I use similar triangles? And our learning goals today are twofold. Number one, our learning goal would be I will be able to rationalize denominators, which just means manipulate expressions such that, I think I should zoom in. Manipulate expressions such that all radicals, those are our square roots, are on our numerators. And those are the top of our fractions. The tops of our fractions. It's a lot of parentheses. Anyway, that's our first learning goal. And number two is an extension because it's part of our CPM curriculum, but it is not one of our state standards. But number two is that I will be able to identify and define Pythagorean triples. Pythagorean triples. Okay, so let's get started. In lesson 6.1.1, we found patterns that helped us determine the length of sides of certain right triangles. And there were two such patterns. One was for a 30, 60, 90 triangle. If we have a triangle which is acute with angles 30, 60, and 90, then all such triangles will be similar to this one. 1, 2, root 3. And the other special triangle, so this one was a 30, 60, 90. Our other special triangle, which is also very common, is a 45, 45, 90. And for 45, 45, 90, all 45, 45, 90 triangles are similar to this one. 1, 1, with sides 1, 1, root 2, 45, 45, 90. So I'll use these a lot today. Okay. First problem. Use the tools we've developed thus far to determine the lengths of the missing sides of the triangles below. If we see a pattern that can be used, we share it with our team. We don't have a team, but we'll be going through this. So I'm just going to look through these and identify any patterns that I see. This is going to be a 30, 60, 90, because 60 plus 30 plus 90 is 180. And this is going to be a 45, 45, 90. I know because it's a right triangle and it's isosceles. So these angles both have to be the same. This one is not necessarily a special right triangle, but I can use the Pythagorean theorem. This one, again, not necessarily a special right triangle, but it is a right triangle, so I can use the Pythagorean theorem. This is a 30, 60, 90. This, I will be using the Pythagorean theorem. This, I will use the Pythagorean theorem. I'm using Pythagorean theorem anytime I have two sides of a right triangle and no angles, because I can't use my special triangle patterns to find missing side lengths unless I have angles. So these last two are also Pythagorean theorem. Okay, first problem, 30, 60, 90. I will do all of my 30, 60, 90 problems at once because I like doing things like that. I like doing all types of the same problem at the same time. Okay, so here we have my hypotenuse is 12 in this problem. So the longest side is 12, and in my original, it's 2. So I noticed that I have a scale factor. 2 times 6 equals 12. I'm going to multiply all of the sides of my special right triangle by 6. So I also have 2 root 3. That's just 2 root 3. That's this missing side because it's the longer of the two. I'm sorry, it's not 2 root 3, it's 6 root 3. Because my scale factor is 6. I'm multiplying all sides by 6. And this one, the shortest leg, I'll multiply that by 6. 1 times 6 is also 6. And it might help you sometimes to sort of turn your reference triangle. Here I see I'm multiplying 1 by 6, root 3 by 6, and 2 by 6. I know they're upside down, but turning a triangle can help. Okay, I have another 30, 60, 90 right here. I'll turn it. Okay, so for this one, I see I'm multiplying 1 by 4. 1 times 4 equals 4. 2 times 4 equals 8. That means my scale factor is 4. And root 3 times 4 is just 4 root 3. So my missing sides are 8 and 4 root 3. Okay, that's all of my 30, 60, 90s for this page. Next, I'll be looking at this 45, 45, 90s. Okay, so this is a 45, 45, 90, but honestly, that doesn't even seem like the easiest way to do this to me because I know if this is isosceles, both of these are the same length, 3 and 3. And then I can just say, oh yeah, 45, 45, 90 pattern is probably faster. I was going to use the Pythagorean theorem, which would give me 3 squared plus 3 squared equals c squared. Square root of 9 plus 9 is c squared. That would be the square root of 18. That takes a long time. And then to simplify that square root, no, thank you. I can just see that my scale factor is 3. 1 times 3, 1 times 3, and this is going to be 3 root 2. Yeah, I think that's easier. Anyway, next one. Do we have any other 45, 45, 90s? That was the only one. So now we're going to use Pythagorean theorem on the rest of these. Okay. Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. A squared plus b squared is c squared. Pythagorean theorem. I'm making another little blue sheet. Length of the leg squared. Okay, this is the Pythagorean theorem. Let's use it. So my legs are 4 and 3, so 4 squared plus 3 squared equals c squared. 16 plus 9 equals c squared. 25 equals c squared. I take the square root of both sides. 5 is c. This length is 5. Okay, next problem. Again, I'm using Pythagorean theorem. So let's see. I've got leg squared plus leg squared equals the hypotenuse squared. It won't always be the hypotenuse that is missing, but for these two it is. So I've got leg squared, 8 squared plus 6 squared equals my hypotenuse squared. Usually we call it c. That's 64 plus 36 equals c squared. 60 plus 34, 64 plus 36 is 100. So 100 is c squared. I take the square root of both sides, and I have 10 equals c. My hypotenuse is length 10. Next problem. Okay, here we have 5, 12, and again, we're missing our hypotenuse. So we'll do 5 squared plus 12 squared, leg squared plus leg squared equals hypotenuse squared equals c squared. That's 25 plus 144 equals c squared. That's 169 equals c squared. So 169 equals c squared. I take the square root of both sides, and 13 is c. Very good. Next. This is a no calculator chapter, everybody. So if you didn't know that this was 13, you could write square root of 169. Okay. Now we have this one. Again, I'm solving for the hypotenuse. I have leg squared plus leg squared equals hypotenuse squared. 3,000 squared plus 4,000 squared equals c squared. Gross. Okay, this is 9 and 1, 2, 3, 4, 5, 6 zeros. And this is 16 and 1, 2, 3, 4, 5, 6 zeros equals c squared. Gross, 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 gross. Okay, this is 25 and 2, 3, 4, 5, 6 zeros equals c squared. Take the square root of both sides, and I get c equals, I think, 5,000. It might be 5,000. If it isn't, you could leave your answer like that. I'm not really sure. If you're wondering how I did these zeros so quickly, it's because I have studied scientific notation. That was part of IM1. While we're not going to learn scientific notation this year, it actually is really important. So I strongly suggest you look up YouTube, all of that stuff, because I don't just know how to do big numbers in my head. I understand how powers of 10 work. Okay. Next problem. 15 and 36. Pythagorean theorem. 15 squared plus 36 squared equals c squared. I do not know what 36 squared is. This will be my final answer. The square root of 15 squared plus 36 squared. Now, if we were allowing calculators for this unit, then sure, you could figure that out. But there's something to be said for the value of leaving answers in exact form and doing what you can by hand reasonably. Okay, next problem. Aha, this is Pythagorean theorem, but it's not the same as the other problems that we've done because we're no longer solving for the hypotenuse. So I'll call this, I don't know, b. A squared plus b squared equals c squared. So I've got 9 squared plus b squared equals 41 squared. Now, I do not know what 41 squared is. I could figure it out, but that's not the point of the lesson. I'm going to subtract 9 squared from both sides. And I have b squared equals 41 squared minus 9 squared. I take the square root of both sides, and I get b equals the square root of 41 squared minus 9 squared. And that is the best I can do without a calculator, personally, reasonably. I mean, yes, I could long form multiply 41 squared. I could probably even find a trick to do it. But again, the point of this lesson is to do what you can do by hand reasonably. Next page. Okay, 6-13. Carla noticed some patterns. Carl noticed some patterns as he was determining side lengths of the triangles in problem 612, the previous problem. He recognized that the side lengths in part C, B, F, G, H, and I were integers. He also noticed that knowing the triangle side lengths in part C could help him determine the hypotenuse in parts D and G. Okay, that's a lot of referencing. All right. D and G. I see. Aha. Smart. Let's talk about that. If you had done C You could have done D and G faster than me. Ha 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 ha. Okay, so in part C, we found a triangle. Part C, we had a triangle that had sides 4, 3, and 5. Part D was another triangle, which was double the size of part C. It doesn't look like it, but just numerically it is. 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10, which is what we got for the hypotenuse. Similarly, down here, this triangle is that triangle, but times 1,000. Which means, look, we got C right. Haha, that makes me happy. Okay, what else did Carl say? Carl also said that parts C, D, F, G, H, and I were integers. All the sides of these triangles were whole numbers. We've got 8, 6, and 10, 4, 3, and 5, 13, 12, and 5, 5,000, 4,000, 3,000. Aha. Okay. So it turns out, everybody, that these are, they're not the same as special right triangles, but they are notable types of triangles. They're these sets of numbers, 3, 4, 5, 5, 12, 13. They're called Pythagorean triples. And they're called that because, in particular, they are right triangles with integer side lengths. We like them because they're easy to work with. The triangle, the 3, 4, 5 triangle is always a nice example to give students, just speaking as a teacher, because if you're solving for 4, you get a whole number, 3 a whole number, 5 a whole number. You don't really need a calculator in order to make these problems friendly. Pythagorean triples, they're just kind of pretty. And then part B asks you to find some other sets of Pythagorean triples, and I will leave this to the reader. I leave this to the reader / watcher. I encourage you to Google Pythagorean triples and see just how many you can find, which also seem friendly. Okay, 6-14. Determine the missing side lengths for the triangles below. Try to use our side length patterns whenever possible. These are our side length patterns. We've got a 30, 60, 90, and a 45, 45, 90. Okay, so this is a 30, 60, 90 triangle with hypotenuse length 13. To get to 13 from 2, I need to multiply by 6.5. So 2 times 6.5 equals 13. We will also have to multiply 1 and root 3 by 6.5. I'm taking my original triangle and I'm scaling it to this one. So we'll have to multiply 1 by 6.5. That's this length. And we'll have to multiply root 3 by 6.5. I'm just going to write 6.5 root 3. I'm taking this triangle and I'm multiplying all of its lengths by 6.5 because the hypotenuse, 13, is 6.5 times this hypotenuse, which is 2. Are there any other 30, 60, 90s? Aha, there's one. Okay, here. Looks more like this. With this one, the shorter leg, the one that matches with the number 1, is now length 7. So my scale factor here is 7. I'm multiplying 1 by 7 to get 7, which means I'll need to multiply my other side. So this would have been 2, but it'll be 2 times 7. So it's 14. This would have been root 3, but it's 2 root 3. I take my original triangle and I multiply by whatever I need to make it scaled version of my original special triangle. Okay, let's look for some 45, 45, 90s. This is the 45, 45, 90. 1 times 25 is 25. This side must also be 25. And then this side down here will be 25 root 2. Okay, here we have another 45, 45, 90. And this one is a little bit harder. Now my hypotenuse, which is root 2, is becoming 6. And that's a little harder to figure out. So I'm going to introduce some algebra, meaning I'm going to introduce a letter and solve for it. So I'm going to say root 2 times a equals 6. And I'll solve for a. That'll be my scale factor. Divided by root 2, divided by root 2. And a is equal to 6 over root 2. But I don't like that. I don't want to have a radical in the denominator, and you'll see why in just a little bit. So for now, I'm going to leave this as 6 over root 2 and 6 over root 2, because that's my scale factor. That's what I need to multiply by 1. But later on, we'll see that this is not the final answer. Okay. These, I don't have any angles given. I don't have any markings to show that I have an isosceles triangle, so I need to use the Pythagorean theorem. I have 2 sides of a right triangle, and I'm trying to find the third. For this one, I have the legs. So I'll say leg squared, 18 squared, plus the other leg squared, 24 squared, equals my hypotenuse squared. I take the square root of both sides to get my hypotenuse. And my hypotenuse is equal to the square root of 18 squared plus 24 squared. And that's as much as I can reasonably do without a calculator. That is my final answer. Okay, now here. This one's a little bit harder because I have the hypotenuse and a leg, and I need to find the missing leg, so I'm going to have to use subtraction. But let's get going. I've got my leg squared plus my other leg squared. This is the length I don't know, equals 52 squared. I subtract 20 squared from both sides. And I get that my leg squared equals 52 squared minus 20 squared. To figure out the length of the leg, I need to take the square root of both sides. And my leg is length, the square root of 52 squared minus 20 squared. And I leave it like that. Okay, next problem. Use your right triangle to calculate the area and perimeter of each polygon. Focus. We've got A and B. So these problems are really nice because they involve breaking things into pieces and thinking. The first thing I know is that a tick mark means all of these lengths are the same, which is not what you would assume by looking at it. Okay, so this is 6 feet, 6 inches, this is 6 inches, 6 inches, 6 inches, 6 inches. And this is a little deceptive, but this piece here must also be 6 inches. Now, I thought this was going to be a 45, 45, 90 triangle when I was just looking at it, but what I really see is that if I blow this up, then what I get is a 30, 60, 90. 30, 6 is here, 60, 90. So the height of this triangle is going to be I multiply the hypotenuse by 3 to get to 6 from 2, so I need to multiply all the sides. So this is 3 root 3, and this is 3. The reason I care about this is because I need to find not just the perimeter, but the area. The perimeter is easy. It's 6 times 1, 2, 3, 4, 5, 30. But the area is not as easy. So to find area, I need length times width for the rectangle part. This is 36 plus, and then the area of the triangle part is 1/2 base times height. So 1/2, the base of this triangle is 6. The height of this triangle is 3 root 3. So this is 36 plus 9 root 3. This is 9 because that's 1/2 times 1/2 of 6 is 3, so that's 3 times 3 root 3, 9 root 3. Okay. This problem was tricky. If you didn't notice the tick marks, you wouldn't have known they meant for this rectangle looking thing to be a square. Okay, next problem. Here we have a 45, 45, 90, and then a square. So in order to figure out the length of the square, I need to figure out the length of the legs for the 45, 45, 90, but it's kind of more friendly than the last problem because the hypotenuse of our standard 45, 45, 90 is root 2. So this is just being multiplied by 6 root 2, which means that this length is 6 and this length is 6. Okay. The perimeter for this is going to be 6 plus 6 plus 6 plus 6 plus 6 root 2. So 6 times 4 is 24. And then plus 6 root 2. That's the best I can do without a calculator, and we're not using calculators in this chapter. The area is going to be 36 plus 1/2 base times height. Let's write it big. So the area of the square is 6 times 6, which is 36. The area of the triangle, you know, I'm not willing to use the formula. I see that this is half of a square. I can reason that. So I'm going to say that it's 1/2 the area of the square. 1/2 of 36 is 18. So I can just add those two pieces together. 36 plus 18 is 14, 54. Do-do-do-do. Yay! Okay, let's learn how to rationalize denominators. Oh boy. So, learning goal. I will be able to rationalize denominators. Meaning, basically, that just means that you're going to be able to manipulate an expression such that all square roots are on the top of any fractions, are on numerators. Period. Sorry, let me see if I can make it better. Okay. So when we don't want to have the square root in a denominator, but we don't want to change the number, we must choose a useful form of the number 1 to make an equivalent form of the same number. Take note, 24 over root 3 times 1 is still 24 over root 3. Okay, I mean, clearly, we're going to use this fact to rewrite our expression in a way that is more standard. So, for example, you know that 4 over 4 is 1. Do you also know that root 3 over root 3 is 1? It is. So I'm going to take this number, 24 over root 3, and I'm going to multiply it by root 3 over root 3, which is just a special way to write the number 1. And this becomes 24 root 3 over, and root 3 times root 3 is just 3. Let's write that on the side. Root 3 times root 3 equals root 9 equals 3. That's why on the bottom I just have 3. Now you're not quite done because 24 divided by 3 can be rewritten as 8, and our final answer is 8 root 3. This little box, I don't know why I put that there. I don't remember. We don't need it. This is the final answer. Let's do a couple examples. We're going to rationalize each of these radicals. First one, 6 over root 3. Multiply top and bottom by root 3. And I get 6 root 3 over 3. This is not the final answer because 6 divided by 3 is 2. So I rewrite this as 2 root 3. I always choose what to multiply by using the radical in the denominator of my original fraction. So this is 12 over root 2. I multiply top and bottom by root 2 over root 2. Well, I multiply the whole thing by 1, and my special one is root 2 over root 2. Anyway, this is 12 root 2 over 2. And that's not my final answer because 12 divided by 2 is 6. So I can rewrite this as 6 root 2. And we have 41 over the square root of 7. Okay, so this becomes 41 root 7 over 7. Now 41 is not divisible by 7, so this is your final answer. Done. Now a harder version of this problem could be, let's see, 41 over 2 root 7. In which case you would still just multiply top and bottom by root 7 over root 7, and you would get 41 root 7 over 14. The only thing you need to multiply top and bottom by is this root 7 piece, because that's what you're trying to rationalize. And I'm going to cross this out because it's not part of the notes, just as a thought. Okay. Here we have a little statement. Why would I want to do this? There are a few reasons why you might want to rationalize the denominator. Number 1, it makes other operations easier, like adding and subtracting. Number 2, it helps to have a common form so that we can communicate with one another about our calculation results. Historically, there was a third reason. So reason number 1, it's easier to add things if you rationalize denominators. For example, this 2 root 3 over 3 plus 3 minus root 2 over 7 is harder to combine than, it's easier than this, but honestly, they're both kind of hard. The real reason we rationalize denominators, as far as I can tell, is for the same reason that if we were to write the number 1/2, we probably wouldn't choose to write 16 over 32, or 100 over 200, or 150 over 300. All of these values equal 1/2, but we write 1/2 because it's more common. It's almost just about being polite. It's about writing in a way that people can understand you. Just like we have a simplest form of a fraction to represent the whole family of fractions that are really have the same numerical value, so too do we have an agreed upon way to write radicals, and that is in numerators, not denominators. Last page. Okay. Summary, special right triangles. 30, 60, 90 right triangle. This is a 1 root 3 2 triangle. The ratio is always the same for 30, 60, 90s. For 45, 45, 90s, we've got 1, 1, and root 2. Recall, sine, cosine, and tangent. Sine of theta is opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tan, opposite over adjacent. These special right triangles are so important that as you work in math, it will get to the point where it's almost like sight words. Like when you read the word the, you probably don't sound it out. When we see sine of 45, we're going to know, bam, that's root 2 over 2. All of these are so common that we have to just know them. So that said, there are ways to know them. Let's look at these. So I'll do the 45s first. Sine of 45. Sine is opposite over hypotenuse. So sine of 45 is 1 over root 2. But we don't write it like that because we rationalize our denominator. So it's root times root 2 over root 2 equals root 2 over 2. That's sine of 45. Cosine of 45 is also 1 over root 2. But we don't write it like that. We rationalize the denominator, and it equals root 2 over 2. Tan of 45. Well, you might remember that tan of 45 is 1, but if you don't, we have 1 opposite over adjacent over 1. 1 over 1 is 1. There we go. Let's look at sine, cosine, and tan of 30 degrees. Sine is opposite over hypotenuse, so we have 1 over 2. Cosine is adjacent over hypotenuse. That's root 3 over 2. Tan is opposite over adjacent. That's 1 over root 3. But we don't write it like that. We rationalize our denominator. So we write root 3 over 3. Sine of 60. Now this is our reference angle. We have root 3 over 2. Cosine of 60. We have 1 adjacent over hypotenuse, 2. And tan of 60. Tan is opposite over adjacent, root 3 over 1, which we just write as root 3. So what did we learn today? Well, we reviewed applying our special right triangles to similar triangles and solving for missing sides. We reviewed using the Pythagorean theorem to solve for missing sides in right triangles. And we defined Pythagorean triples. And we identified sine, cosine, and tan for all of the angles in our special right triangles. That was a lot. Okay, well, thanks so much for your time, and I'll see you next time. Bye.